Hi, everybody. Welcome to our final stoichiometry Mount Moleville video, where we get to explore black diamond problems. Oh my gosh, can you see how all of Mount Moleville has turned into, look at it all. It's all black diamonds now, just about. Evidently, it must have got very icy. That's what happens when it becomes hard. Um, But I also wanted you to see some of the runs have changed their names, and these are some of the actual concepts that we're going to take a peek at in today's video. But please feel free to take a look at the blue square video or the green circle video and get yourself up to speed to these black diamond runs, all right? Because otherwise you could be like that cartoon over there, kind of like, oh my gosh, I've done double green squares, let's go for it. And these might seem really overwhelming to you. So if any of these problems we do in this video seem overwhelming, please go back and check out the previous videos. So what are some black diamond stoichiometry topics? So this one is a little bit of a review, but it is a question that seems to be a jump to the black diamond, because it's the same problem that I gave in the blue square problems, where I was asking people to calculate an empirical formula from this data. But now the question is, what's the molecular formula? So it's one more step, and that's generally what makes black diamond problems. We ask you to do one or two more steps in the stoichiometry trails that you're having to go through, and it makes it a little more complicated. So from the blue square video, we recognized that we could turn all of these percentages into grams. And then once we had them in grams, we could turn them all into molar amounts on our way to an empirical formula, which is the key to answering what is the molecular formula for this compound. And by dividing by the smallest number, we will get whole number integers that will produce our empirical formula. But now comes this little twist. If I want to take this empirical formula and turn it into a molecular formula, I need a very important piece of information that would have to be given to you in every problem. I would need this molar mass of the entire molecule, not just the empirical formula, but the entire molecule structure. And using this, I know that my molecular formula must be some multiple of this empirical formula, since the empirical formula only weighs 30 grams per mole. How much more do I scale it up? Just take the entire molecular mass, molar mass, and divide it by the empirical formula's molar mass. And notice that this is 6 times bigger to get to 180 grams per mole. And therefore, all you have to do is take the empirical formula and multiply it by 6, every coefficient in the empirical formula by 6, and you end up with this C6H12O6 formula as the molecular formula. And what's really cool is that is the general formula for all sugars, or I should say a lot of sugars. So this happened to be the formula for our fructose in our previous blue square stoichiometry problem session. So now I know the true molecular formula, but keep in mind, none of this information will tell me how the 6 carbons, 12 hydrogens, and 6 oxygens are actually oriented in the molecule, but at least I know how big the whole molecule must be at this point. Okay? Cool. So let's take a break at empirical formula camp for a second. Yeah, way up there. And let's make some hot cocoa. Hot cocoa, yum. Okay, so when I make hot cocoa at empirical formula camp, these are the supplies that are generally up at the camp. I follow this recipe, okay? Usually we have these beautiful, yummy packets of instant hot cocoa mix. I know, but remember, you're at the top of the Mount Moleville camp, so it can't be too fancy. And then we have these bottles of water around, and it only takes a half a bottle, for every 1 mug to produce 1 yummy mug of hot cocoa. So what do I actually have up there right now at Empirical Formula Camp? What's in the cupboard waiting for me to use up there? Well, this is what we have. And I want to know what we have so I can make enough mugs of hot cocoa for all of you to enjoy. So how many mugs can I make? Well, when I got to the top of Empirical Formula Camp, there were 4 packets of hot cocoa mix, 3 bottles of water, and 6 mugs lying around. So with these quantities just lying around in Empirical Formula Camp, the question really becomes, how many mugs of hot cocoa can I actually make? So looking at this and the balanced reaction known as a recipe for making hot cocoa at my camp, theoretically, I should be able to make 4 mugs of hot chocolate with 4 packets. If I have only 3 bottles, I might be thinking, oh, I can only make 3 mugs. But nope, look up, I only need a half a bottle. So I can make, if I used up all of the 3 bottles, I could make a total of 6 mugs, which is great because I have 6 mugs of available. I can make 6 mugs. So I should be able to make 6 mugs of hot cocoa, right? Wait, I only have 4 packets. So the maximum amount I can make is 4 mugs of hot cocoa. Now you might be saying, Nick, that was such a simple problem. I could figure that out anytime. But what I want you to recognize is this is the approach that we will take to determine the amount of product that you can make in any reaction, is that we have to take stock in the amount of each reactant. And then the amount of each reactant, we will figure out how many products we can make with each one. And in doing so, we'll be able to determine the limiting reactant based on the limiting amount of reactant that shows me the fewest amount of products I can make. So that makes my packets of hot cocoa the limiting reactant in this problem, and it makes the water and the mugs that I have up at the camp the reactants in excess. Try not to make anything harder than it looks just because all of a sudden it becomes chemical. So when I throw this problem at you, you might be thinking, oh my God, look at that formula. What's going on up there? I have no idea. So pause. You can figure this out. The beauty of this is that I've given you the recipe, sort of, and I've given you the amounts that you have of at least 1 sulfuric acid, H2SO4. But the beauty of this problem is I've told you that you have excess sodium hydrogen carbonate. So that means this is not a limiting reactant problem, because excess sodium hydrogen carbonate will react with all of the sulfuric acid to produce the product that I want to make. In this case, I'm looking at carbon dioxide. And you might be asking, why should I care about this? This is not mugs of hot cocoa. What's this? This is chemistry. Oh, but the beauty of this reaction is it is something that you've seen around a little bit. Sodium hydrogen carbonate is baking soda. Wow. Sodium hydrogen carbonate is baking soda. And that was a bunch of white baking soda solid dumped on some sulfuric acid with a little orange food coloring kind of mixed in with it. So that's all those bubbles that you see. Those are all the moles of carbon dioxide that are being released. And you might have played with this when you were a kid with vinegar and baking soda. It's quite fun, as long as you do it safely, okay? In this situation, they were dumping tons of that baking soda. So this is the situation where they had excess baking soda being dumped on this very limited pool of sulfuric acid. Okay, so how can we solve this problem? One of the things that will make the problem simpler and take all the text out is I highly recommend that you put little keywords underneath your reaction, like I know that in this problem, I'll be able to get moles of sulfuric acid because I've been given a molarity and a volume. What am I trying to solve for? put a little molecules question mark underneath CO2. And now you can focus on only those two species in the entire problem. It narrows the focus of the problem. All right, take a second to try to solve this. You can pause the video, and then I'll show you how I figured it out. All right? Cool. We're back. Ready? I had a little note there. Always make sure the equation is balanced. I need a balanced equation similar to my hot chocolate recipe where I had a half a bottle of water was needed. These things are important if I'm going to try to convert from one species like sulfuric acid to CO2. Is it really a 1-to-1 ratio? This is the balanced equation. And if you have any questions about how I came about this balanced equation, please go back to Blue Square video where I show how to balance reactions. Okay? Now, for every 1 mole of sulfuric acid, I produce 2 moles of CO2. This is the dimensional analysis method I use. I highly recommend it. Okay? And in this process, I start with the 25 milliliters of sulfuric acid I was given in the problem and start trying to convert and cancel units until I end up with units of molecules of carbon dioxide. So notice here, I even put in the unit of milliliter conversions so that I can change that to liters, so that I can change and cancel the molarities, liters of solution, with the liters in the problem. A lot of you will try to just take that out, do it in your head, not show it. But remember this, you are actually showing this math, not just so you can get the right answer, but so that we as instructors can see how you're doing the problem. And if you botch a milliliter liter conversion, at least we can see that, oh, you just multiplied by 1,000 instead of divided by 1,000. So please show these, and they will help prevent you from making mental mistakes in those heats of battle moments called midterms. Okay? All right. So at this point, if I stopped, I would end up with moles of sulfuric acid. So now I want to cancel moles of sulfuric acid. And so I use the mole ratio from the equation to get me to moles of carbon dioxide. And then I can change moles of carbon dioxide using our friend Avogadro's number to get to molecules of carbon dioxide. So a very long dimensional analysis problem is what makes this a black diamond problem, okay? An easier problem would have stopped maybe with just moles of CO2, or just stopped somewhere or figured something out maybe with just sodium sulfate, okay? This is not the only way to do this problem. I want to make sure that you see another possible dimensional analysis method you might have used where, and again, I often use, where I actually focus on the molecules of CO2 in the answer up there and really want to put that as my very first ratio, that I have to have a value somewhere in the problem that gives me molecules of CO2. And the only way I have it, since it's not H2SO4, the only place I get it is Avogadro's number. So really it's just starting with molecules of CO2 as the first unit in your dimensional analysis problem. And now your goal is, ooh, I got to cancel moles of CO2. Oh, I use the mole ratio from the balanced equation. And as you'll notice, everything cancels out similar to the problem above. Wait, yeah, milliliters and milliliters. Sorry, I was getting happy canceling. And I end up with exactly the same answer if I multiply across and divide by the bottom. So there's no one special way to do dimensional analysis problems. The goal is to make sure that you show how all the units cancel to produce the units of your final answer. All right. Now, what if, oh no, there wasn't a huge excess in that video, for example, of dumping tons of solid sodium hydrogen carbonate. What if you only had, say, 10 grams? A limited amount of sodium hydrogen carbonate to neutralize and react with the sulfuric acid. And then to make the problem a little different, what if I just, okay, we won't go for molecules of CO2. We'll step back a second and go, what if I just wanted to know moles of CO2? So again, now in the problem, I can write, I know moles of each reactant. I can figure out moles of each reactant, and I'm trying to figure out moles of CO2. Okay? Take a second, see if you can try this one, and tell me how many moles of CO2 could this reaction possibly produce. Pause the video. Cool. I hope it didn't take too long, but we're back, and I want to show you, again, the same process I used for making hot mugs of cocoa. I'm going to follow here. I'm going to start using dimensional analysis and figure out if I were to react all of the sulfuric acid and chew it all up, all 25 milliliters, how many moles of CO2 could I make? 0.17 moles of CO2. Now, if I were to react and chew up all the sodium hydrogen carbonate completely, and then figure out if I chewed up all that sodium hydrogen carbonate, all 10 grams, how many moles of CO2 could I make? The reason I like this problem is because the answer is being solved in both dimensional analysis problems. There are different ways to figure out limiting reactants. This is not the only way, but at least right in front of me now, just like the mugs of hot cocoa, I can say if I used up all the sodium hydrogen carbonate, I'd be able to make 0.12 moles of CO2 maximum. There's no way that I could make that 0.17. No way. Because sodium hydrogen carbonate, using it all up, could only make 0.12. So, what's the limiting reactant in this problem? It's the one that's getting completely chewed up. That is our sodium hydrogen carbonate. And that's the limiting reactant, which means when you do this reaction, you will have excess sulfuric acid when you're done. And boy, you don't want to start washing your hands in that, thinking, yeah, it's all neutralized, it's not acidic. Oh my God. This reaction is very, very, shall we say, undone. So sulfuric acid could react with you, and you might want to find some more sodium hydrogen carbonate to help chew up the excess sulfuric acid that's still around. To make it a black diamond problem, I could ask you how many moles of sulfuric acid are in excess. Okay, that could be a fun problem to try. Let's try this one. Take a second, pause the video, and then let's see what you guys come up with. Cool, we're back. I hope you had fun trying this problem. How many grams of copper are possible theoretically if you reacted 1.5 grams of iron with 50 milliliters of a 0.500 molar copper sulfate solution? So again, I've given you two amounts for us to figure out, again, moles and moles of each of these species. And the question I'm trying to ask is how many grams of copper sulfate? So by doing this again, writing it under the reaction, you no longer maybe need to read the entire problem all over again as much. All right? This is how I figured it out. Again, I start with the copper sulfate and see how many grams of copper I can produce if I were to chew up all of that copper sulfate up there. So if it all gets chewed up, I'd make 1.59 grams of copper sulfate. Now I pay attention to the 1.50 grams of iron. And if I chewed up all the grams of iron, how many grams of copper could I produce? I would be able to make 1.71 grams of copper. So which one is limiting? Which one is in excess? Right? I can only make 1.59 grams of copper theoretically, maximum, at the most. That's it. I could never get to 1.71 grams. So what is limiting? It must be the copper sulfate solution up there, okay? Because that's the maximum amount I could make. Now, we are actually going to do this in lab 1 this term. This is a reaction we're going to do, and we're not going to be quite sure about what this mole ratio is in this reaction, but this is one possible recipe that could take place. But no matter what reaction takes place, and any reaction we do in lab, it is very rare that you will get 100% efficiency, 100% yield, and produce 1.59 grams of copper. So last semester, a student made 1.35 grams of copper. And the student was beating himself up like, oh, I made errors. I lost copper. I suck. I'm never going to be a chemist. Stop. Percent yield, 99% of the time, is a reflection of how well that reaction wants to actually make product. How well do those molecules actually want to bump into each other and change places with one another? It has very little to do with you as a chemist. Sometimes it does. Sure, I could have spilled half my copper on the bench somewhere. So keep that in mind. But oftentimes, it's not a reflection of you at all. It's a reflection of the efficiency of the reaction and how well it wants to make product. But let's figure out what is the percent yield for this reaction. So to do percent yield, you want to take the actual mass that you produced in lab and divide it by the theoretical mass that if the reaction went to completion, perfect, everything went amazing, the reaction was efficient to 100% degree and you didn't spill anything or lose anything, then we can do this math. So I would take the mass, divide it by the theoretical, and multiply it by 100 to turn it into a percentage. And for this student, she made 84.9% yield. Again, she was beating herself up about this, but that yield is very, very good. That reaction is very, very efficient. Or there were things in her reaction that actually added mass to her final product. And she really didn't have 1.35 grams of copper. She had less, but something else was in there adding mass and making it look like she had more. So in lab, please keep track of not only things that you could, that would actually lose mass in your product. Please keep track of things that might add mass to your product and make your yield too high. That can happen too, okay? You have just completed all 3 videos, or at least gone through them all. This is all the black diamond, blue square, green circle stuff I can give you. Obviously, there's more out there. That's why I've given you all these websites to go play with. And definitely ask us questions about it. And we'll play a little bit more in lecture with stoichiometry during the first week of the term. Okay? I hope you have fun playing on Mount Moleville, and I'll see you soon. Bye.